So we're continuing with kinematics. So lecture 2. Still kinematics. So the outline for today is we're going to have a quick recap of the definitions we introduced last time. Then we will introduce the kinematics equations. Kinematic equations. That will be algebraic. Then we will discuss the graphical way of talking about things. So graphical analysis of 1D motion. And that will be it for all one-dimensional motion. For the rest of the class, today is 3-hour lecture. So for the rest of the class, we will work on the first worksheet. That will be some kinematic problems in 1 dimensions to get you to practice these ideas, and we can work through them together until we get familiar with them. Then tomorrow and for the rest of the week, we will discuss two-dimensional motion, which will require vectors and a slight generalization of the math we work with in 1 dimensions. Okay. So let's get started with what we have. So the quick distinction we mentioned last time briefly is that we have vectors and scalars. Vectors and scalars. So a vector is a quantity that has both magnitude and direction. So it tells you something about where you're going, not just by how far or how much speed you're going. It tells you also the direction. So a vector has both magnitude and direction. And by magnitude, we just mean a size of the vector. So examples of this are displacement, which we denote by the symbol delta x, the change in position, or velocity, which is v with a vector, acceleration, letter A with a vector on top, and there is also momentum, there is force. We will cover those when we get to them. On the other hand, we have scalars. So a scalar has magnitude, but no direction. So examples of scalars include distance, which sometimes we denote by the symbol d if it's the path length or the total distance traveled, or sometimes we denote it by the magnitude of the displacement, which looks like an absolute value of the vector, but it's really the magnitude of the vector, not just the absolute value, which will become important in 2-dimensional motion. So it's just the original vector with 2 vertical bars on it. Or sometimes we just write it as delta x without the vector at all, but this is more accurate. And then there is speed. Speed, you can either write it as the vector v with two vertical bars, or we just write it as v without any vectors on top to just denote the magnitude. Same with the magnitude of acceleration. Magnitude of acceleration, that's just the vertical bar of the acceleration, or sometimes we just write it simply as a. And again, as I mentioned last time, whenever I write these three bars on top of one another, this means defined as or equivalent to, as opposed to the two horizontal bars, which mean equal. Okay, those are vectors and scalars. And then we had some definitions. We defined what the elapsed time is. We defined what the velocity is, what the speed is, what the acceleration is. So we're going to quickly review those. So time and elapsed time. So time is a fundamental quantity. We don't know how to define time in anything more fundamental than what it is. So we define it operationally by how we measure it. So we define time by observing changes in physical phenomena. We look at the sun repeats its motion, and then we define a day depending on that. We look at a pendulum, it swings back and forth, and we define a second based on that. We look at like how atoms change, and then we define like we make an atomic clock out of that. So it has to be a repeating process, and this repeating process, we use it to define a unit of time. But really what we can talk about is the elapsed time. So the elapsed time, it's more physical in a sense. We denote it by delta t, and delta is the Greek letter that we use to indicate change. So it's the change in time. And this is defined as the final time minus the initial time. Delta t must always be positive. It cannot be negative, but t initial and t final, those can be positive, negative, or zero, because these only indicate where, these only indicate when we started our stopwatch. So a negative t initial, for example, would be something like BC. So some historical event happened and it was some year BC, that's negative time. And then AD, that's positive time. And then right at zero, that's just where we chose to put our stopwatch. So these are arbitrary, these are conventions, but the physical quantity is delta t, it's the change in time. And because time only flows forward to the future, this quantity is always positive. Good. Okay. Then we have displacement. Displacement and position. So displacement is the change in position. So we denote it by the symbol delta x and with a vector on top because it's a vector. This is defined as the final position minus the initial position. In one-dimensional motion, sometimes we just drop these vectors, but if you want to be accurate, you should indicate the vector as well. So x initial, this is the initial position. or initial location, and x final is the final location. And we used a coordinate system to indicate the location. So this is a coordinate system with 0 as the origin. This is the positive axis, positive x-axis, and this is the negative x-axis. So you can have x initial starting here, for example, and x final be there. Then the displacement would be from the initial to the final point, and it's a vector with its tip pointing toward the final position. Okay, good. With displacement and time, we use these two quantities to define the average velocity. So the average velocity, we define that to be the average. It is defined as displacement over elapsed time. And we discussed that this doesn't take into account what happens in between because it only cares about the initial and final points. So if you went to some place and spent time, but you came back to the same position, then it doesn't matter. It will be average velocity equals 0. But average speed was different because average speed took into account the total distance or the path length. So the average speed, I didn't denote it by any special symbols because I don't want to confuse it with the v, which we use for velocity. So I just call it the average speed. And this is defined as the path length divided by the elapsed time. So the average speed is not in general equal to the average velocity. Okay, good. Okay, so one step forward, we have time, we have displacement, we have velocity, we have speed. The next natural object is the acceleration, or really average acceleration. Average acceleration. This is A average, and it's defined as the change in velocity over elapsed time. In the same way that the average velocity was the change in position over elapsed time, the acceleration is also the change in velocity divided by the elapsed time. During this course, we will be using acceleration, like constant acceleration, and in that case, the average acceleration will be the same as the acceleration itself, like instantaneous acceleration. So at some point, we will drop this symbol average, and we will just write A. But for now, let's keep our definitions accurate. So this is the average acceleration, and it's defined as the final velocity minus the initial velocity divided by the elapsed time. Good. Okay. So all of these quantities are averages. So average velocity, average acceleration, average speed. But sometimes it's really useful to get a quantity that describes an instantaneous acceleration or instantaneous velocity or instantaneous speed. For example, when you're in your car, your speedometer reads an instantaneous speed. It doesn't give you an average speed. It gives you an instantaneous speed. So how does that work? This works by taking the average over really small times. So this delta t that we have, we can make it smaller and smaller and smaller. Like take the average over 1 second. or even better, take the average over half a second, or even much better, take the average over 1 millisecond, 1 nanosecond, whatever. Like, make it as small as you can. Ideally, it should approach 0. And in that limit, the value of the average quantity approaches a finite value. This finite value is the instantaneous value. So this wording we denote by the mathematical symbol of the limit. So let me add another page here. So instantaneous velocity. This one we denote without any subscripts, average, or any, it's just v. And it is defined as the limit. This is the mathematical symbol for the limit, as the time goes to 0 of delta x over delta t. This is just a fancy way to describe what we just said, that take an average, but make the time shrink. And when the elapsed time shrink, this approaches a finite value. This finite value is the instantaneous velocity. We will not use this definition, but we should have an understanding of what it means. So instantaneous velocity, and in the same way, instantaneous acceleration is exactly the same definition, but we replace the word velocity by the word acceleration. So say acceleration. This becomes v. Okay. So one thing that we want to mention is that when the acceleration is constant, so it doesn't change as time goes on, then the average acceleration equals the instantaneous acceleration, because it doesn't change. So it doesn't matter if you take an average or not, it doesn't change. So in that case, we can just use the definition of the average acceleration and use it as instantaneous acceleration. Okay, so this will be important when we derive the kinematic equations now in a second. Good. One important conceptual point before moving on is, what does it mean to accelerate and what does it mean to decelerate? Because in English, when we say acceleration, we usually have in mind speeding up. But that's not accurate. You can have acceleration that slows you down. And you can have acceleration that speeds you up. So we need to clarify that. The direction of acceleration, right? Let's see, how do I want to write this? Speeding up versus slowing down. Okay. So we have one-dimensional motion, so we have 4 cases. The direction of motion is defined by the direction of the velocity vector. So if the car is moving, so this is motion. If the car is moving to the right, that means its velocity vector is to the right. But that doesn't mean the acceleration vector is to the right. That's different. Velocity is what tells you the direction of motion, not acceleration. So in that case, if we have a coordinate system that says positive is to the right, this is the positive x-axis, then this velocity will be positive because it points to the right. In that case, if you have the acceleration as well being to the right, then the acceleration is positive, and yes, you're speeding up. You're accelerating in the same way you're moving, so you're speeding up. But if you have the acceleration to the left, then the acceleration is negative, and you're slowing down because it's opposing your direction of motion. But you can have a different scenario. You can have, here is the positive x-axis, here's the negative x-axis, but the car could be moving to the left. This is the direction of motion. So in this case, velocity is to the left because this defines what the direction of motion is. So it's negative. If the acceleration is to the left, acceleration is also negative, but the car is speeding up. It is speeding up to the left because the acceleration is in the same direction as the velocity. And if it's positive, pointing to the right, the car is slowing down. So really, it doesn't matter if the acceleration is positive or negative in an absolute sense. What is physical is the relative direction between the acceleration and velocity. This is what matters. This is the physical criterion we have. Because positive and negative is a convention. This is just a coordinate system we choose to work with, but the relative direction, this is physical. This will be true for any coordinate system, whether you choose positive to be right or negative to be right. That doesn't matter. The direction, the relative direction doesn't change. So this is worth summarizing. So let's see. So let's see. Speeding up is when you have the acceleration and velocity in the same direction. So these are two different cases. So I want to separate them like this. So speeding up to the right. Here, speeding up to the left. You're speeding up to the right, you have both velocity and acceleration being positive. If you're speeding up to the left, you have both velocity and acceleration being negative. Then we have the same concept, but for slowing down. So slowing down. Now we have the acceleration different from speed, from velocity. So this is now slowing down, but motion, motion to the right. So moving to the right, and here moving to the left. So this is the physical picture. Doesn't matter if the acceleration is positive or negative. It only matters what relative direction does it have with respect to velocity. Good. Do we have any questions on this point? Okay, if we don't have any questions on this point, we will move on. Let me give you, let's work out couple of examples. So, examples. It will just apply the definitions that we have. So, example 1, we want to calculate displacement, distance, and acceleration. So let's see. Suppose we have a truck that moves from a certain initial position to a final position. So we have, again, our coordinate system, positive x, or I can just call it x in kilometers. And the truck moves from x initial equals 4.7 kilometers all the way to a final position that is 6.7 kilometers. Okay, so here this is the initial position of the truck, and this is the direction of motion. This is actually the displacement vector. So this is delta x here. It's moving, this is direction of motion. So we want to calculate displacement, distance, and acceleration. Displacement is straightforward. It is by definition. We have delta x is defined as final position minus initial position. In this case, the final position is 6.7 kilometers, positive, minus 4.7 kilometers. So that is just 2 kilometers. And it's a positive number because it points to the left. It points to the right. Distance, in this case, is the same as displacement. It's 2 kilometers. There was no U-turns. There is no difference in the direction. So distance is also 2 kilometers. And distance is always non-negative. So displacement can be positive or negative, but distance is always non-negative. For acceleration, we don't have enough information, so we need more. We need some information on how fast the cart was going and how long did it take to cover this distance. So this is given in the rest of the example. So we have, suppose the truck accelerates from rest. So it starts from initial velocity equals 0. That's how we translate from rest to a final velocity of 30 kilometers per hour. We have initial velocity and final velocity. And that took the truck 20 seconds of its motion. So delta t, the time it took, is 20 seconds. And we want to calculate the acceleration. So again, we just use the definition. The average acceleration is defined as the change in velocity by the elapsed time. And the change in velocity is v final minus v initial divided by elapsed time. We just need to convert the units now because we have a discrepancy in the units. We have here kilometer per hour, and we here have seconds. So we need to either convert hours to seconds or seconds to hours? In this case, it is more convenient to convert hours to seconds, because acceleration is naturally measured in meter per second squared, meter per second, so we just denote that by meter per second squared. So we will convert velocity from kilometer per hour to meter per second, and then use the definition. Good, okay, so let's see. Velocity is equal to 30 kilometers per hour. I will multiply by a conversion factor to remove kilometers and make them meters. So that would be 1,000 meters and 1 kilometer in the denominator, because this is just 1. And then to remove hours, I will multiply by 1 hour in the numerator, divide by 60 minutes in the denominator, and then for each minute, we have 60 seconds. Okay, and now the units cancel. So we have kilometer cancels with kilometer, hour cancels with hour, and minutes cancel with minutes, and we are just left with meters per seconds, which is what we want. So I need more space here. So that becomes 30 times 1,000 times 1 over 60 times 1 over 60. Then you can use your calculator as meter per second. This will give you, let's see, what does it give? 8.33 meter per second. 8.33 meter per second. Good, now we have the right units. We have the velocity in meters per second, and we have the time in seconds, so we can go ahead and calculate the acceleration using this relation here. So we have the average acceleration now is equal to final velocity is 8.33 meters per second. Initial velocity is just 0. And the elapsed time is 20 seconds. So this is just 8.33 divided by 20, and the units are meter per second squared. This evaluates to 0.417 meter per second squared. This is a positive acceleration. Velocity was also positive. That means the cart or the truck was speeding up throughout the process, which makes sense because it starts from rest and it gains speed until it gets to 30 kilometers per hour. So it must have been speeding up. That's the only logical way to get to that velocity in that time. So that's consistent with the fact that we got a positive acceleration with a positive velocity. Okay. Let's see. Let's take another example. Just reverse the direction. So what did I call this? Okay, let's call this example 1. The other one is example 2. Okay, now we have the same truck, but on its way back, we have the same coordinate system with x measured in kilometers, and we have the initial position of the cart now is 5.25. I didn't write the units because I included the units here on the axis already, so there's no need to write it again. It would be redundant. I might have done that before, but it's not necessary. 3.75, that's the final position. So the card starts here, and it goes from this initial position to this final position, so motion was to the left. If motion is to the left, then velocity is negative. That's just by construction, because it's the change in position divided by the elapsed time. Elapsed time is always positive, but the change in position will be negative because you're going to less and less values of x. So velocity will be negative. But acceleration can be positive or negative. We don't know yet. That will depend on the fact, that will depend on the details. Was it slowing down? Was it speeding up? How long did it take? So that will be given later as information. But for now, we can just calculate the displacement and distance. The displacement vector points from the initial position to the final position, and as you can see clearly, it points to the left. So this is delta x. So it makes sense to get a negative answer for that because it points to the left and we defined the right to be positive. Here, delta x is equal to final position minus initial position. In this case, final position is 3.75 kilometers. Initial position is 5.25 kilometers. So that means delta x is equal to negative 1.5 kilometers. See the negative sign? It's there to indicate the direction. And it came out naturally because we have the consistent definition and we substituted in the right formula. How about the distance? In this case, distance doesn't care about which direction you took. Distance will just be positive 1.50 kilometers because you covered that much meters or kilometers. No matter whether you went to the right or to the left, that doesn't matter for distance. Okay, that's all we can do with the information given. Now, with extra information, we can calculate velocity and acceleration as we did in the last example. So in this case, suppose that on its way back, the truck is moving at 30 kilometers per hour to the left. So we have the initial velocity equals to negative, because it's moving to the left, 30 kilometers per hour, which we just converted above to be 8.33 meters per second. So I can just write that here without repeating the calculation, 8.33 meters per second, again with a negative sign. The final velocity is what? Let's see. It then decelerates and takes 8 seconds to stop. The fact that it stopped means that final velocity is 0. And how long did it take to stop? It again took 8 seconds to stop. From that, we can easily calculate the average acceleration as delta V divided by delta T, V final minus V initial divided by elapsed time. So V final is 0. Initial, know that there are two negatives here now. There is a negative between VF and V initial, and V initial itself is negative. So negative 833 meters per second divided by the elapsed time, which is 8 seconds. This is a positive number because you have 0 minus minus, that's a plus, 8.33. So that's 8.33 divided by 8 meter per second squared, which gives you 1.04 meter per second squared. A positive number. Motion was to the left, so velocity was negative. Acceleration is positive. That means the car slowed down during that time. And that makes absolute sense because it was moving from 30 kilometers per hour and then it stopped. So even though the acceleration is positive, the car is slowing down. So if I would draw the acceleration vector, it would be pointing to the right here. That would be the acceleration vector. And the velocity vector would be going to the left here, which is consistent with the fact that when you have relative opposing vectors, acceleration and velocity, you get slowing down. Okay. That's all for the definitions. See, these are all definitions. We haven't derived any equations yet. We just defined quantities, we defined displacement, we defined velocity, we defined acceleration, and we gave examples on them. We now want to write equations to help us solve problems. So let's see. Do you have any questions before starting the next part? Check. You guys have any questions? Okay, good. I have to find the solution to this chat problem. I couldn't do it last time, but I have to find the solution to that so I can see when you have questions. Okay, let's continue then. Also, feel free to unmute yourself and talk if you have questions, since the chat is not working. Okay. So this is part 2, which is kinematic equations. 1D kinematic equations with constant acceleration. I will write down 3 equations and then derive them. But those 3 equations are of absolute importance. So if I were you, I would memorize them because these come up a lot. I mean, I will give you a formula sheet at the end when you have exams and stuff. But these are so important that if you have them memorized, it will be much easier to solve problems because you have them in your head. So you can write them down and see what equations are necessary, what equations you need, which one is relevant, which one is not. So instead of just going back and flipping pages until you get to the equation you want. So I'll write 3 equations. Those are the main kinematics equations. So first one is V final is equal to V initial plus A delta T. V final is the final velocity. V initial is the initial velocity. A is the acceleration. In this case, it's constant, so there is no need to make a distinction between average or constant, because it's average anyway, and delta t is the elapsed time. And of course, this is a vector equation, so the signs matter. The second equation is delta x, which is the displacement, is equal to v initial times delta t plus half the acceleration times delta t squared. Those are really the main two equations. The third one is derived from the first two by eliminating delta t. So by taking delta t from one equation, substituting it into the other, and eliminating the time, to get an equation that doesn't depend on the time, which can be useful for problems that don't give you the time explicitly, just gives you distance, acceleration, and velocities, then it becomes useful. But in any case, it is v final squared is equal to v initial squared plus 2a delta x. In this equation, I haven't written down the vectors. Here, vf squared doesn't really distinguish between positive or negative velocity because it's squared. So if there is a negative, it will just go away. For acceleration and displacement, you should have them as vectors. So I can write them as a delta x, and this is a dot product. So it's a little bit more advanced to the level of this class. So that you really should have it as a dot product between two vectors, which is the projection of acceleration along displacement, but we don't care about that here. We will only care about positive or negative direction. So if acceleration is positive and displacement is positive, you get a net positive quantity. If both are negative, you also get a positive quantity. If they have relatively different sign, you get a negative quantity. So these are the main kinematic equations. Let's see. So these are very important. Essentially, any problem we need to solve in kinematics will use one of those, or more than one of those at a time. So what I'm going to do now is derive each one of them, and then we will have our first worksheet to get some practice with these. So I will number them just to refer to them when deriving them. So let's enumerate this. This becomes 1, 2, 3. Okay. So derivation of equation 1. This is the easiest one to derive because it really comes from the definition of acceleration. We have the average acceleration is defined as delta v by delta t. And when we have constant acceleration, when a is constant, the average acceleration is the same thing as the acceleration itself. So we can really, therefore, these three dots mean therefore. So a is equal to delta v divided by delta t. You can multiply both sides by delta t, so that gives you a times delta t is equal to delta v. But delta v is defined as the final velocity minus the initial velocity. So this means when we substitute this here, you get a delta t equals V final minus V initial. And then you can rearrange the equation to get, like, add V initial to both sides. So you get V final equals V initial plus A delta T. So it's really a rearrangement of the definition of the average acceleration and using the fact that average acceleration is equal to acceleration when the acceleration is constant. This equation is important when you have the initial velocity, the acceleration and time, and you want to calculate the final velocity. Or you have the final velocity, acceleration, and initial velocity, and you want to calculate the time taken. So you will be given 3 variables and you're solving for the 4th. Okay. We then derive equation 2. Remember, this was equation 1. We then want to derive equation 2. Let's see. So how to derive this one? Let's see. Okay. Here we use the definition. Here we use the definition of average velocity. So the average velocity, we defined it as delta x divided by delta t, right? So we can rearrange that, multiply both sides by delta t. So we have V average times delta t is equal to delta x. But at the same time, the average velocity is, you can, if you took any statistics class, it's the initial velocity plus the final velocity divided by 2. Like when you're taking the average of 2 numbers, let's say you're taking the average of 3 and 5. You have 3 numbers, 3 and 5, and you want to get the average of these 2. You know it's going to be 4, but to do it systematically, you add 3 plus 5 and divide the result by 2. So you get 8 divided by 2, that's 4. So the average, so we defined it kinematically, but there is also a statistical definition, which is V initial plus V final all divided by 2. Okay, so we're going to combine these two definitions. We have V average here and V average here equal to that. So I'm going to just substitute. And then I get V initial plus V final all divided by 2 and all multiplying delta t equals delta x. Okay, good. I can do a little bit more simplification by just distributing this delta t inside and taking the factor of half outside. So delta x becomes half V initial delta t plus half V final delta t. This is just distribution of the bracket. Good. So far, so good. Now I'm going to use the equation I derived earlier, which is this one, equation 1. So use equation 1. How am I going to use it? I'm going to replace this V final by V initial plus A delta t. This is the equation I derived, equation 1. So I'm going to use that to replace V final by V initial. So that gives me the following: half V initial delta t plus half, open bracket, V initial plus A delta t times delta t. And then let's play with the algebra here. So you again distribute this delta t inside, and you also distribute the half. So you get half V initial delta t plus half V initial delta t plus half A delta t, right? Half V initial delta t and half V initial delta t, it's just one V initial delta t because you're adding half of the same quantity. And these two delta t's here become delta t squared. So I finally get delta x equals V initial delta t plus half A delta t squared. Okay, so this is the derivation of the second equation. By the way, when you're doing problems, you're not going to need to derive any of these equations. I'm just showing you where they came from, so you don't just memorize them blindly without understanding what these mean or where they came from. So now we derived equation 1, we derived equation 2, and the last one is equation 3. We will derive that now. Any problems so far with the derivations? Okay, then I will assume that there is no problem, so we can move forward. And again, if you guys have any questions, you can always unmute and ask me. So derivation of equation 3. Let me rewrite equation 1 and 2 because we are going to use them now. So V final equals V initial plus A delta t. And equation 2 is delta x equals V initial delta t plus half A delta t squared. Equation 3, which I want to derive, is V final squared equals V initial squared plus 2A delta x. And at this point, I'm going to drop the vector notation because it might be confusing in this derivation, because again, it requires dot product and stuff that I don't want to discuss in this class. So I'm just going to use the plus and minus notation for the direction. So the first thing you see in this equation, which we want to derive, is that it doesn't have delta t in it. This means we want to eliminate delta t from the first and second equations. So I'm just gonna substitute delta t from the first equation into the second one to eliminate it. By that I mean, from equation 1, we can rearrange this equation as follows. We can write it as V final minus V initial equals A delta t, and then divide both sides by A. So V final minus V initial divided by A is equal to delta t. Okay, so I got what delta t is in terms of other variables. And then substitute in 2. So each time I see delta t, I'm going to remove it and plug in Vf minus Vi all divided by A. So I get delta x is equal to V initial times Vf minus Vi divided by A plus half A Vf minus Vi divided by A, and then the whole thing squared. The rest is algebra and manipulation. So I can distribute this Vi inside. So that becomes Vi Vf minus Vi. That's just Vi squared divided by A. That's the first term. The second term is something squared. So when you have a fraction squared, you square the numerator and the denominator. So we get Fa times V final minus V initial squared upstairs, and then A squared downstairs. So far, so good. We have an A upstairs and A squared downstairs, so one of these will die. We will just have an A left. So that becomes Vi Vf minus Vi squared divided by A plus half Vf minus Vi squared divided by A. And I can write this half as 2A in the denominator. Good. Great. The next step is to expand the square bracket. So we have V final minus Vf all squared. To expand the bracket, you square the first term, you square the second term, and you have the cross term twice. So that becomes V final squared minus 2Vf Vi plus Vi squared. Because when you square a negative number, you get a positive number. And then we substitute that in there. So delta x becomes Vi Vf minus Vi squared divided by A plus a big fraction divided by 2A, and this big fraction is Vf squared minus 2Vf Vi plus Vi squared. The next thing I want to do is to have the same denominator, so I will multiply up and down by 2 in the first term. So I will add a 2 here and a 2 there, which is equivalent to multiplying by 1, so nothing happens. And then I have the same denominator. And up there I have 2 Vi Vf minus 2 Vi squared plus Vf squared minus 2 Vf Vi plus Vi squared. As you can see, those cross terms cancel. And I have negative 2 Vi and positive Vi squared. So that gives me negative Vi squared. So that becomes V final squared minus V initial squared divided by 2A. So if we multiply both sides by 2A, we get delta x divided times 2A is equal to V final squared minus V initial squared. And then you can rearrange that to get V final squared equals to V initial squared plus 2A delta x. This is the third equation. As you saw, it doesn't come from anywhere other than the first two equations. So in a sense, the first two equations are the fundamental equations, and the third one is derived. But in many times, it is useful to get an equation that doesn't have the time in it. You can, of course, only stick to the first two, but that will make your derivations longer sometimes. Okay. Good. Let's take a little break. Let's take a 15-minute break before coming back and starting the activity, so you don't get overwhelmed, because we covered a lot of content, and I think I might want to postpone the graphical analysis of 1D motion to either tomorrow or to the end of the day, but not now, because we already covered a lot of content. So I just want you to get familiar with the kinematic equations, the 3 kinematic equations. So let's take a break and come back at 9:30.